Hey, Science 8's Manchak here with your next lesson in our progression through Unit D. And in this lesson, we are going to cover Concept D2, which is all about complex machines, and it should be relatively quick and not too terribly complex, I hope. Pun completely intended. So at this point, you should have completed Concept D1. Which had you go through the video lesson, do some practice work like questions out of the textbook, maybe the worksheet for this concept, as well as doing an activity related to simple machines where you've been touring around your house and trying to find examples of simple machines in your house. So if you've done all of that, done your formative quiz, and then finished your summative quiz, then you are ready now to move on to Concept D2, which is this concept. So I'm going to introduce that now, and here we go. So in this concept, we are going to describe what complex machines are, what systems and subsystems are as well. We are going to analyze a mechanical device, and we'll look at a couple of them in order to try to figure out what it does for us, describe the contribution of individual components or subsystems to the overall function of the device. So we're going to try to pick out some of the simple machines that are being used in a bicycle, because I think everybody can relate to a bicycle. I hope you can. And then identifying the components that operate as simple machines. So these two will kind of work together. Then we're going to talk about identifying the source of energy for some familiar mechanical devices. And then that'll link into some stuff that we do a little later on in the unit as well. We'll describe what linkages and gears are, and then we'll have a look at linkages and power and transmissions in a mechanical device and describe their general function. So that's our goal for this concept. Just a couple of notes for you, and this will be just above where you found this video in our Google Classroom. The textbook pages are going to be listed there, so if you wanted to go into your textbook and read through that stuff as well, you can. We also have some videos associated with this concept. If you watch only one video, watch this one on gear basics. I think it's fantastic, and it gives you some practical examples of how we use gears to help us do the work that we're trying to do and make machines far more efficient for us, putting in less input energy and getting more output force out of them. So I think it's a great video to have a look at. There will be some practice questions you can work on. There's a worksheet you can work on. As always, you'll do a practice quiz. Wait for feedback before you move on to the D1 summative quiz, which will be coming at the end. So without further ado, we are going to scroll down and jump into our conversation on, if I can find it here, this is me not showing being prepared right now, on Concept D2. So I will hit present and we will get started. So we've gone through all of these already right at the beginning of the lesson, so I'm going to scroll down to the next one. So complex machines. Within the last 200 years, scientists, engineers, and inventors have developed machines that use sources of energy such as coal, oil, and electricity. Large supplies of energy combined with new materials and technologies caused an industrial revolution. And you've probably studied this at some point or will be studying it at some point, what the Industrial Revolution is all about. But basically what happened during that time is we discovered that we could make some more complex machines that are powered not just by animals or humans anymore, but we can power them using steam and then ultimately the combustion or burning of certain chemicals like coal or later on gasoline and diesel and natural gas. And so that Industrial Revolution, which started, I'm just going to say in the mid-1800s, saw, once we've got our more powerful machines, that large factories became more common because these powerful machines could mass produce goods. In other words, they could make lots of stuff for really quickly with minimal input of energy. And so the newly invented steam engine allowed the transport of goods and people across countries in record times. And so in other words, to get goods from point A to point B didn't take days or weeks any longer. It took, hours or days to get them, depending on how far you were traveling, which is pretty impressive. And so that kicked off a whole bunch of inventions and other sort of complex technologies. Now, I should say, and I want to be clear about this, that we've been using complex machines far before the Industrial Revolution. As people started to bring certain structures together, we started to get those more complex machines. As we brought one simple machine with another simple machine and brought them together into a device, we ended up with two simple machines working together to accomplish a task. That's a complex machine. So, anyway, going back to the Industrial Revolution stuff, people had access to more food, clothing, tools, and raw materials than ever before. So we started to see some changes associated with that. So that's your little history lesson here. So since the Industrial Revolution, the development of new technologies has continued at a rapid pace. I mean, even in my lifetime, we did not have cell phones when I was born. That was not something that happened. Computers were really not a big part of our lives back then, but we have now started to combine all of those things and make much more complex machines than we did before. Today, we are almost completely dependent on machines. And think of the things you enjoy doing. So whether it's whether it's riding a skidoo, or whether it's going and doing a sport, anything along those lines, there are machines that are involved in what you enjoy doing. So can you do any of these things without a machine? And maybe you could. It's quite possible you could. I mean, even think of farming. Could we do the level of farming that we do today without having a complex machine? I don't know. Could we? How would your life change if you didn't have machines? So if you wanted to, take a moment to hit pause and think about that, or track somebody down in your house and have a conversation about how machines are involved in your lives. So complex machines then, let's define what they are. Complex machines are devices made up of several simple machines working together. And several in this case for me is going to mean two or more simple machines working together to make a machine itself. And remember, a whole idea behind a machine is that it is a device that makes our lives easier in some way. A complex machine is a system in which these simple machines work together. And so let's define what a system is. A system is a group of parts that work together to perform a function. So if you've got a lever and you've got a wheel and axle working together in a machine, you have a complex machine, and how those two work together is called a system. Okay? And then that last little note at the bottom there is what I just said a moment ago. Remember, a machine's job is to make our lives easier. In other words, if we want to get to the nitty-gritty of it, they try to make the input force that we need to make an object move. They reduce that input force to make that object move in most cases, or they make things happen faster, or they transfer energy in a particular way, or they change the direction of movement, or something along those lines. Remember those bits that we talked about in concept D1 right at the end. So just a couple of examples of really simple complex machines that I'd like you guys to have a look at. So scissors are actually complex machines because they involve two simple machines. They involve a lever with the fulcrum in the middle, and this is where your input force would be, and this is where your load would be. So there is a first-class lever involved, actually two first-class levers involved in a pair of scissors, and then there is a wedge involved, right? Because you have the need to actually cut the paper. So I've got a pair of scissors here, right? So remember, my input force is where my hands are going to be, and my output force is where the wedge is located. And I don't know if you can see it on this, but there is a wedge on both of these levers. And remember, the wedge is meant to focus force onto the point of the wedge. Whole purpose behind a pair of scissors is to make it easier for us to cut something, okay? To make a nice straight cut along a piece of paper, usually, or some other sort of thing. It might be kind of fun for you right now to stop and to think about how a stapler involves two or more simple machines. Okay, I'll give you a hint. There's a lever involved in the stapler, and it's a second-class lever that we use. But there is at least one more simple machine I can think of in a stapler. If you want to at some point, fire me an email and say, hey, I think I figured out what the other simple machine is in the stapler. And we'll see what we can come up with. So what I want to do now is I want to use a bicycle as an example of a complex machine. And I'm using a bicycle because I think everybody can relate to it. Most people have a bicycle at home that they can look at to try to find these things. So it's a good example of a complex machine because there are several subsystems that work together in that larger system. And the whole purpose behind a bicycle is to move us forward at a faster speed than we could walking. Okay, I think that's the very basics of a bicycle. A bicycle is a more efficient way for us to get from point A to point B because it allows it to happen faster. Okay, so several systems work together to move you forward at different speeds and allow you to turn and help you to stop. Okay, so all of these things are working together to make what we call the modern bicycle. Before we do into this, let's define what a subsystem is. A subsystem is a group of parts that work together to perform a specific task. So on the bicycle, there's lots of tasks that are happening, right? There are the pedals and wheels that their task is to transfer the force from your legs to the wheels so the bike goes forward. Okay, so that would be a subsystem. There's a subsystem involved on the bike that allows you to stop the bike, and that would be the brakes. Okay, and the brakes use a lever, and we'll get into that in a second. There are some gears on the bike, which are part of a wheel and axle system that allow you to move the bike faster or slower, put in more effort or less effort, depending on how quickly you want to go. So, and I've just outlined a few. There may be some more systems on your bike. I didn't talk about the steering, right? And how the steering works. That would be somewhat of a wheel and axle system as well, but I didn't talk about that in this slide. So the brakes, for example, are a subsystem that's used to apply force to the wheel itself to slow the wheel down. And when you squeeze the brakes, you're using a lever. And it's a first-class lever because your input force is where you squeeze the brakes. There's a fulcrum in the middle, and then there's an output force on the other end that actually causes a change in a cable to press the brake pads into the wheel itself. And there's another lever involved around the brake pads. Okay, so there's a bike is a complex machine. There's one subsystem that's using two levers. Okay, the pedals also act as levers to increase the force you apply to the wheel and axle that your pedals are attached to. Then we have a chain that fits into where if your pedal is here and it goes around like this, that spins a chain, and that chain or spins a gear, and that chain transfers energy from your legs to the gears at the back of your bike, which spins the larger wheel itself. And we're going to talk a little bit more about gears as we move on later, but let's define a gear as a structure that allows us to reduce the force you need to apply to move forward. And they work as part of a wheel and axle, and they're considered to be a wheel and axle themselves. So we've got several kinds of gears, especially on a mountain bike. Looking at a bike like this, so we talked about the lever systems that are involved in the brakes of your bicycle, right? Where else on your bike are we finding examples of simple machines, right? This is obviously a complex machine. I mean, there's a wheel and axle at the front here. There's a wheel and axle at the back here. We talked about our chain that goes through this system here. Pedals are a lever of some sort with a fulcrum, right? So if you wanted to try to dig around and see if you can find any other examples of simple machines in this complex machine that is a bike. So that's an example, of a complex machine and all the little simple machines that go together to make that complex machine do the task that it's supposed to do. What I wanted to do is, because we mentioned this subsystem here, which involves the pedals, the chain, and these two sets of gears, the front gears and the back gears, I wanted to talk a little bit about mechanical devices that transfer force, okay? Because we are transferring force here. As you pedal, we are applying force to the pedal here. That force is being transferred through the lever as a load to move the load that is this gear, this wheel and axle that we've got right here. And then by moving that, we are transferring force from where the pedals are to this back set of gears, this back wheel and axle, which transfers force again to the larger wheel itself and causes the bike to go forward. So it's complex when you start to think about it. So I wanted to talk about these subsystems that produce motion, and we call them linkages or transmissions. And let's define linkage. A linkage is the part that transfers your energy, in the case of a bike, to the back, from the pedals to the back wheel. And the actual linkage is the chain, because it is the thing that links the pedals to the wheel in the back, and the wheel and axle in the back. So many machines use high tension belts or chains to rotate objects. And all you need to do is look under the hood of your car. And a lot of you, I know, like fiddling with cars and other devices like that involve engines or motors. Well, there's going to be belts involved in that. If you like RC cars, there's belts involved in that. All of those are linkages, where we're taking energy from one spot and transferring it to another spot. So you may have seen the fan belt that transfers energy from the engine to spin the cooling fan in your car. The fan moves air through the radiator to keep the engine from overheating, and it's driven by a belt that is transferring energy from one spot of your car to another spot. Chains or belts form a direct link between two separate wheels, so that when one wheel turns, the other will turn, and in the same direction. Okay, so that we can spin something in a larger, more complex machine. If one wheel is larger, it will rotate more slowly, but with a greater force than the smaller wheel. And what's going to happen to the smaller wheel is it will rotate much more quickly. So if we have a big wheel driving a small wheel, what's going to end up happening is one turn of this big wheel is going to mean many turns of this small wheel. Okay? And if we have it the other way, small wheel here, big wheel here, one turn of, or many turns of this small wheel is going to mean one turn of this big wheel. We're going to talk about that. That's the whole essence behind gears, which we'll get to in a second. So this is a system that transfers force, and I've already talked about this, right? We have a chain wheel at the front. This is where your pedal would attach, so you'd apply force to this pedal, and the pedal would go around and around, and through a lever function, which would cause the chain wheel to move, and which would then cause the chain to move, which is then going to cause the gears at the back here to move as well. Okay, I'm not going to get into the gear ratios and those kinds of things just yet with this example, but I want you guys to see that we are transferring force with the linkage here that is the chain. Okay, so the chain is allowing us to transfer force. A transmission is a special type of linkage that tends to move larger loads. So this is an example of what a transmission in a car or a truck might look like. And a transmission contains a lot of different gears that allow the operator to apply a large force to move an object slowly, or a smaller force to move an object quickly. And I want to break that apart for just a second. We have gears in our transmissions that basically allow us to get the car moving. Getting the car moving means that we need to apply a large force to move the object, the car, forward. Once we get the car forward, we can start to move from applying large force to smaller force. Once we get an object moving, it is experiencing inertia. So an object in motion tends to remain in motion. And so we can apply smaller and smaller forces, but we can get the object to move more quickly. And so as you move through the gears, from stop to, let's say, highway speed, we're moving from applying large force to move the car slowly, but to get it moving. But as the speed increases, we don't have to apply as much force, but we can apply force to get the car moving more quickly. So as you shift from first gear eventually into fifth gear, first gear is all about getting the car going and getting at least started. Fifth gear is all about applying a little bit of force, but keeping that speed up that we've maintained with the vehicle. Transmissions are similar to gears on a bicycle, except that they're designed to transfer much larger forces. And so they're much more complex than the simple gear system we would have on a bicycle. In a car, the driver can select a low gear to get the car moving and then change to higher gears when driving down the highway. And those higher gears are designed to apply a little bit of force, but allow us to increase our speed as we get up to those higher speeds. So we've talked a lot about gears here. And gears are essential components of most mechanical systems because they allow us to do a bunch of different things, which includes increasing or decreasing speed or transferring the direction of energy or direction of force being applied. But simply put, a gear is a wheel, an axle, with teeth on it, okay? And these teeth interlink. They mesh together as the gear rotates, okay? And I wish I would have brought some gears home from school so I could show you a little bit, but I didn't do that, so sorry. When the teeth rotate together, one wheel transfers turning motion and force to the other, okay? So if this is the gear that's actually exerting the force, and this one is just sitting here and resting, then we're transferring force from this one to this one as it turns, okay? What you need to understand about gears is that the larger gear wheel, if they're not the same size, the larger gear wheel rotates more slowly and the smaller gear wheel rotates much more quickly. So the larger gear wheel moves more slowly than the smaller wheel, but it rotates with a larger force, okay? And vice versa. The smaller gear wheel rotates more quickly, but it rotates with less force, okay? Gears can be used to increase or decrease speed in a machine, and they can also be used to change direction of motion in a mechanical device. So I don't know if you guys are familiar with this device right here. This is an egg beater or a whipper, but it's not one of the electrical ones. It's a human-powered one. And so what you would do is you would hold on to this handle at the top here if you've never used one of these. We have one at my cabin, and I used to love using it when I was a kid. I don't know why. I'm strange that way. We have a place to hold with one hand here, and then we have basically a pedal, right? This is basically a pedal going on here, and there's a large gear here, which is linked to a smaller gear that we can't see in here. And so there's two purposes of this machine, right? This is I would call it a complex machine because there's a couple of wheel and axles, there's a lever here, right? This large gear is going to spin, and when you spin that large gear, okay, because it's transferred or attached to a smaller gear at the bottom, what's happening is it's causing the small gear to spin many times for every large or one crank of the big gear. So what that's going to do is this small gear is attached to the two whisks at the bottom here, or whippers, let's call them whippers because that just sounds fun, at the bottom here, and so these are going to spin many times for every one time that we spin this large wheel. The other thing that the gear is doing for us is transferring motion that is this way, so spinning on this axis, and it's turning the motion into spinning on this axis. So we're applying force like this, but the force is being transferred and changing the direction of motion to this direction. So it was spinning on this axis, now it's spinning on this axis. I hope that makes sense. So this simple egg beater is doing two things for us. The gears are increasing the speed of the whisks at the bottom because one rotation of the big gear means many rotations of the small gear. And it's changing the direction of motion. So what is normally spinning on this axis is now spinning on this axis. Hope that kind of makes sense. Simple machine, a complex machine, but a simple device is doing a lot of different stuff. I think it's kind of neat. So let's talk about how gears work. Almost any device that contains spinning parts is going to use gears. So you could stop and you could think about things that have spinning parts. They're often going to be using gears. Gears are important in mechanical systems because they control the transfer of energy in a system. For example, in our bicycle, they control the transfer of energy from the rider to the wheels. In our bicycle, we are always going to be transferring energy from the rider to the wheels, but how much energy we transfer and what our bicycle does with that energy is dependent on how our gears are set up. If you're in a low gear, and if you've ridden a mountain bike before, you know that in a low gear, what you're doing is your wheels or your pedals are pedaling in a high gear, your pedals are pedaling really fast, but you're not moving very quickly at that point. And that's the part that's designed to maybe get us up a hill to make it a little easier for us. In a low gear, what we're doing is we are putting a lot of energy into spinning that pedal, and what that's doing is it's transferring a lot of force to the rear wheel, which is going to make us go much more quickly. Okay, so we've got an advantage that's being gained by those gears. Gear wheels work together in gear trains of 2 or more wheels. So, right, you've got one set. This is a gear train, but if we added another one over here, we've expanded the train to 3. The gear has force applied to it. The gear that has force applied to it is called the driving gear. So in our bicycle, the gear attached to the pedals is our driving gear. And then that driving gear applies force to another gear called the driven gear. And the driven gear are the gears located on the back wheel of your bicycle. Remember, the chain is in between, providing a linkage, but you could just as easily have those touching together. It just would make it a little more complicated to arrange a bike as a result of that. This video that I have the link for here is a video on how a manual transmission in a car works. If you wanted to watch it at some point, just go into the Google Classroom and have a look at the resources videos section for concept D2, and you can check that out there. So I'm going to go back to the egg beater again because we've kind of talked about this already. If the driving gear, so that would be this example, this gear right here, is larger than the driven gear, which is this little guy that we can't see down in here, the turning speed in the system increases. So in other words, every one rotation of this will be multiple rotations of the small one. So that is increasing the speed. So when you're to rotate the larger one, it rotates the smaller gear several times. Thinking about the egg beater, the driving gear, which is the one that we are applying the force to, is larger than the driven gear, which is hidden inside here, which rotates the beaters. And so the beaters, or the whiskers, or the whisks, or whatever you want to call them down here, are moving much faster, many more rotations of these than we're getting over here. So gears like this increase the rotation of the driven gears, and we call them multiplying gears. Okay. In reducing gears, the driving gear is much smaller and has fewer teeth than the driven gear. And this reduces the speed but increases the torque or the force. So an example of this, in a bicycle, the gear wheels don't mesh directly with each other, but we have a linkage, the chain, that allows us to link that. And when you shift gears, you move the chain from one gear to another. When you are working on a high gear, on the front end, your driving gear is very small, and on the back end, your driven gear is very large. And so what's happening is we may be spinning a bunch of times with our driven gear, but that is applying more torque or force on the driven gear, on our wheel. That's going to help apply more force to allow us to go maybe up a hill in that case. So I would encourage you at this point, because I've talked about gears and I've waved my hands around and I've moved the mouse around a bunch, go please and watch this gear basics video. If you don't do it right now, do it after I finish the next slide, because it is excellent and it's going to show you some examples of what we can do with a large driving gear and a smaller driven gear, or what we can do with a smaller driven gear and smaller driving gear and a large driven gear. Go check it out. It's a great video. I think it's fantastic. One more thing. Complex machines that make our lives easier, that's what they do for us. This Rube Goldberg machine that you're going to see, a Rube Goldberg machine is basically just a whole bunch of simple machines combined together in a very complex, overly elaborate machine that really doesn't make our lives a lot easier because it took forever to set up. I think you guys might enjoy this. It's set to music, so if you've got some time, it's about 4 minutes long. Check out this video as well. So that's the end of concept D2. I've talked about everything you guys need to know. At this point, it's time to get some practice done, some of your formative assessment or formative work done. So please have a look at the questions on page 276 of your textbook. Please jump in and have a look at worksheet number 2, complex machines. You'll find that in the resources section for Unit D, resources, notes, and worksheets. And then the key to this is also up there under resources, worksheet keys. Okay, you can track that down. Once you've done that stuff, watch the videos, feel like you're comfortable, jump into the practice quiz for this concept, and do the quiz, please. Once you've done the practice quiz, please make sure you hit submit, and then wait for me to give you some feedback on how the practice quiz went. And I like to give you the feedback first, please, so that you can correct any mistakes you might have made before you move on to the next concept, okay? Or before you move on, pardon me, not to the next concept, but to the summative quiz. Then you move on to the summative quiz when I said it's okay to do so, and after you've read through your notes one more time just to make sure you're grasping everything. Hey, and then wait for my results, and then we can move on to concept D3. So I hope all of this has made sense to you. If I've confused you in any way, by all means, check out the videos and then fire me an email and let me know, hey, I'm confused by this, or pop by for my office hour. I do those every day, and ask your questions at that point. I hope you guys are staying healthy, and we'll talk again in concept D3.